Hey guys, I'm Eric at AeroGuard Flight Training Center, and today we are going to do the first part of a two-part video on weight and balance. So in today's video, we're going to focus on kind of the why. Why do we care about doing weight and balance, and what are the effects of weight and balance? And the second video we'll do is kind of the how to calculate weight and balance. So in this example, we're going to dive right in and talk a little bit about the effects of weight on our aircraft, and then the effects of balance, which is the center of gravity, the location of the center of gravity, and how that affects our aircraft. So let's dive right in and get started with the effects of weight. Okay guys, so let's jump into the effects of weight on our aircraft. So I kind of have this divided up into two particular parts. So the first we can talk about is performance. When we talk about performance of the aircraft, we can give a few examples of this, but I think the easiest ones to identify would be, for example, takeoff and landing distances. So if we imagine two aircraft, the exact same model, one is just very heavy, maybe close to its max gross takeoff weight, and the other is very light. They both have the same amount of total thrust in a given scenario and total power, and therefore, in the case of, let's say, for example, taking off, if they both applied full power, they're both going to have the same amount of thrust, but that thrust is either pushing or pulling less weight or more weight. So obviously if it's heavier weight aircraft, it would take longer to get up to our rotation speed, and therefore a greater distance, and therefore a longer takeoff roll. After taking off, we would also maybe see the same effects for climb performance as well. This would be the same if we exceeded our maximum weight limitation, right? So if we went over our maximum weight, then that would only become more accented. Landing distances, also similar, but instead of thinking about power in this case, I would apply it more to braking performance, right? So after we land, if we had the same airplane in a light configuration versus a heavy configuration, the heavier airplane is once again going to take longer to come to a stop. Over to the other side. So outside of performance effects of weight, we also have load factor to consider, and I kind of call that load factor more generically, but we know that it would have an effect on our maneuvering speed, or VA. The higher our weight is, the higher maneuvering speed can go, which is kind of interesting. But the other effect is if we go overweight, right, we have the ability to then possibly cause damage to the aircraft, right? So our aircraft, as we know from what VA is, has certain structural limitations as to how much load factor, for example, the wings or any other part of the aircraft can support. The higher the weight is, the closer or the easier it is to sort of exceed those limitations. So that is certainly another thing to keep in mind with weight. The reason why we have a maximum gross takeoff weight is to ensure that we don't exceed the structural limitations of the airframe. So ideally, we now have a better understanding as to why it's so important to ensure at least that we stay under our maximum gross takeoff weight every time that we go out on a flight. Because exceeding it could change or to unexpected takeoff distances, or could affect the structural stability of our aircraft. Excellent. So now let's jump over and talk a little bit about center of gravity placement and why that's so important to our aircraft. So now let's talk about the effects of center of gravity placement. So what I have here are two aircraft. Theoretically, they're identical aircraft. They're the same weight, they're the same everything. The only thing that's different is the location of the center of gravity. So to show that, I've marked the CG here with that little circle that's shaded. That's kind of the standard mark for the center of gravity, and I've tried to illustrate that the weight falls from that center of gravity, and here the weight is 2,000 pounds, the weight on the other aircraft also 2,000 pounds, and simply the arm between the center of pressure, or the center of lift, and where that CG is located is the only bit that's changed. In the case of this blue aircraft, it's, we'll say, 10 inches, and in the case of this green aircraft, it is 5 inches. I've then also included an arm between this tail downforce that we need to keep the airplane flying level as being the same distance from the center of pressure in both cases, right? So approximately 100 inches in both cases. And these numbers are just made up. This is really just to keep the math really simple, and it's not necessarily specific to any airplane. So what is this trying to show? This is referring to how the aircraft would remain balanced in flight, right? So this weight that's coming down on one side, if we kind of imagine, I know it's a little bit backwards, but if we just imagine that the center of pressure or the center of lift is kind of like a fulcrum or a pivot point. I know in reality that's the CG, but for our purposes right now to illustrate the concept, we're just going to imagine that the fulcrum is here. We can imagine then that this weight is pulling down on this side, and then our tail down force is producing a force on the opposite side. And really what we want to do is create a balance or an equilibrium. So we know that the weight, this 2,000 pounds, is going to produce a rotational force in this direction. We can calculate that rotational force by multiplying the force that is being exerted multiplied by the arm, or that distance. So 2,000 times 10 is 20,000 pound-inches of torque or rotational moment this direction. In order for the airplane then to remain balanced, we need the same torque in the opposite direction. So that means 20,000 pound-inches the other way. So if I know the arm is, let's say in this example, 100 inches, then I know this tail down force. In this example, then I could just do the math backwards. So 20,000 divided by 100, and we will get that the tail down force in this case is 200 pounds. Okay? Great. So we've kind of set this aircraft in its equilibrium state. Let's jump over and try to compare it to the green airplane now. So in the green airplane, same deal, right? Same weight of the aircraft, but now the arm is shorter. The CG is closer to the center of pressure, or the center of lift, meaning the CG is more rearward. And in that case, if we multiply once again the force times the arm, we get a total rotational velocity or torque of 10,000 pound-inches. And so to do the same on the opposite side, we end up with the same 10,000 pound-inches divided by the 100-inch arm, and we get the tail down force to be 100 pounds. Okay, what does that mean? So if we compare these two, there's one thing that I think really quickly stands out, and that is the tail down force is obviously different for each of these aircraft. What does that mean, or how does that affect anything? Well, if we have more tail down force, that means the total down forces are going to be greater, which means we're going to have to produce more total lift. If we have to produce more total lift, right, they're the same exact airplane and we're comparing them, then this blue airplane has to produce more total lift. That means for any given power setting, we're going to end up having a higher angle of attack, which also means more induced drag. So overall, we're going to fly slower, right? We're going to have less performance with a more forward center of gravity. As opposed to when we make the CG more rearward, now our total down forces are less, so we have to produce less total lift, and therefore, for any given flight condition, we'd have a relatively lower angle of attack compared to this blue airplane, and therefore less drag is created, and we'd have generally better performance, right? So by having a more rearward CG, we can anticipate being able to fly faster for any given power setting. Next, one thing we may not immediately see that stands out here, but is really important, is both of these aircraft are in this sort of state of equilibrium where they are both balanced. However, this aircraft has total forces up to 20,000, and this has half that amount, which means this entire system, right? If you think of it almost like a seesaw, right? That's pivoting around. if we had a seesaw that had two really heavy people on either side, it would be really hard for you as an outside force to move it. But if you had two small kids on each side, then you could probably move it without issue. Nothing is really any different. This would be like having the two heavy people on either side of the seesaw. It's a lot of force in both directions, so it's a lot harder for an outside force to move it. In this case, those outside forces could be the wind, it could be our flight controls, whatever. But the point is, it's more resistant to those outside forces, and therefore having a more forward center of gravity generally means the aircraft is more stable. It's harder to move it out of its regular condition. Whereas when the CG is more rearward, we have less total torque, and the result of that is just like the two kids on the seesaw, it's easier for an outside force to move, which means inherently the aircraft is less stable. So I think this hopefully helps clarify why it's so important. Obviously, if you take the CG too far forward, we could get to a place where our stabulator or our elevator is unable to really effectively control the pitch of the aircraft. Vice versa, if we take the CG too far aft, for example, to a place where it's almost equal to the center of pressure or the center of lift, we could get to a place where we have basically no stability. And so it's important that we keep it in the specified range from the manufacturer. Good. So hopefully this helps elaborate as to why we want to calculate weight and balance before every flight and how important each of those factors really are. Stay tuned. We'll keep going with the next round, kind of showing how to calculate weight and balance for a normal general aviation aircraft. Don't forget to like and subscribe, and we'll see you in the next video. Thanks.